This is our circuit that we wanted to measure the RPMs of a drill chuck with. We'll have an apparatus that goes into the chuck, and as it spins, we have a sensor that will measure a frequency from that sensor, and will output that frequency to this circuit, which has a Schmitt trigger on it to clean up the frequency, and that will be our sensor frequency that will be inputted into our circuit. Now for testing in the lab, we are simply using a frequency generator to replace the sensor frequency for the sake of demonstration. What happens is once that signal is fed into the circuit, it processes it and outputs an RPM reading on the display, and it does so in several stages. This circuit outputs a latch and reset frequency that tells this counter when to start counting the high points of the sensor frequency, and then the latch signal tells it when to display that counted number at a time that it would display the RPMs. It follows this pattern here, where we have the RPM sensor goes into a Schmitt trigger and outputs a sensor frequency into the counter and display. Then the clock circuit outputs a reset and a latch signal to properly time the counts, so the number you see here regularly refreshing is an accurate representation of the RPM. Our tests say that we get from 0.17 to 0.22% error. This is the clock signal that's produced. It has a high time, a low time, and it oscillates at a certain frequency. The higher time goes from here to here. This frequency is processed into a reset and a latch signal. The reset uses an RC circuit to generate a pulse at the leading edge of the high time of the clock frequency. This reset frequency tells the counters when to begin counting. So at this point, it would tell the counters to reset their count to 0 and begin counting, and at this moment they would reset to 0 and begin counting again. The latch frequency uses an RC circuit as well as 2 NAND gates to process the clock frequency, and it generates a high time frequency that dips down to a logic of 0 when at the trailing edge of the clock frequency. This is fed into the display circuit to freeze the numbers during the high time and to load the numbers that have currently been counted on the low point. So from this period, it sets the count to 0 and it begins counting the pulses from the sensor frequency, and at this point it will display the counted number. Therefore, the number that you see on the RPM display is to measure the oscillations that was counted across this time interval right here.
So this is some of the math behind this. This equation represents the high time of the clock, which over there is the square wave, and it controls how long that counter is counting to send to the latch. This is your counter circuit. We actually have 2 of them, one for the clock and the second for this lab experiment. We've set up a simulating circuit to simulate the sensor frequency from the physical input device, and for the sensor input is controlled by this, for its frequency, it's controlled by this equation, so that we can control and test to see if our meter is accurate as to if it displays the right quantity for a certain frequency of our input. This is the equation for that sensor frequency in relation to the RPM of a drill chuck. We have the revolutions per minute, and through this dimensional analysis, it's going to be this is going to be your sensor emitter frequency. So this frequency will go down into the counter, and it will be counting through the high time of the clock, and it will be displayed as the number that will represent the RPM on the display. So as you can see on this frequency generator, or on the frequency, we're at 7.47 kilohertz, and we are registering at 9,901 or 9,900 RPM. So what we'll do to confirm this is we will take our 7460 hertz and multiply it by our high time, which currently is 1.33 seconds, and we get an RPM of 9,921. So it's within a 20 to 21 variable from that number.
Before we get into some test demonstrations, I'm going to show you what the different latch and reset functions do. I'll remove both of them, and you can see the counter rapidly counting up all of the pulses from the sensor frequency. If I connect the reset frequency, you can see that it will reset. It's resetting back to 0 based upon regular intervals. So you can stop at 7 about here. It's not making it all the way up. If I put on the latch, you can see that it freezes it and it updates at regular intervals. If I remove the reset, it's going to keep counting up, so then the latch will just freeze it wherever it happens to randomly fall in the counting. When I put the reset on, it's calibrated to freeze it at a number that represents the RPMs given a corresponding sensor frequency. Now if I toy with the frequency representing the sensor frequency, and it changes the RPMs. So for 1163, we have a frequency of 0.877 kilohertz, or 877 hertz. 877 hertz represents 1,169 RPMs, and right here you can see that we have 1162. So it's very accurate. We found that the temperatures of the capacitors in the timing circuit made the largest difference in the count, ranging it up to over 0.5% error rather than our normal 0.03 to 0.22%. You can see as I adjust this further, the value will change to other numbers as well. And this remains fairly accurate in the lower RPM. For 581 RPM, we have a reading of 438 hertz, which represents 584 RPM. You see this is 581 within 3 RPM of the actual RPM.